My research group at Oregon State is interested in the applications of new materials, and one of the questions we've asked ourselves is, could carbon nanotubes make a better solar cell? When you see solar cells on someone's roof, they're probably made out of silicon. So the sunlight's been absorbed by this crystalline material and turned into electricity. But there's a lot of other materials that could be used to make solar cells. Gallium arsenide's a great example. You'll find that on most of the satellites up in space. It makes a lighter weight solar cell with a higher efficiency, but it's more expensive. You can also make great solar cells out of perovskites, organic molecules, quantum dots, and many other materials. So before we try to make a solar cell out of something new like a carbon nanotube, we should ask ourselves, are there any fundamental limits we're going to be up against, and what new things can carbon nanotubes offer? In the 1960s, Shockley and Quasar did a calculation estimating that only 33% power conversion efficiency is possible in any single junction solar cell under unconcentrated sunlight. And this limit that they calculated could be even less if you don't have the right band gap of the material. So is there any way we could beat this limit that Shockley and Quasar calculated? Is there a material that would go above this 33% line? To answer that question, we should look in more detail about the assumptions that are made in the Shockley-Quasar calculation. So this box represents any of the materials I showed you before, silicon, gallium arsenide, and all the others. And a photon gets absorbed by that material, and an electron and hole pair are created. That means an electron's excited in the material, it becomes free to move through the material, and it leaves behind an empty spot called a hole. So this electron and a hole are used to charge a battery or do some other useful work. And that's the basics of how a solar cell works. The key here is that one photon was turned into one electron-hole pair. And that's the key assumption that Shockley and Quasar put into their calculation. What if there's a material that this assumption doesn't hold true, where one photon maybe could make more than one electron-hole pair? So let's have a look at what might happen in carbon nanotubes. It starts out the same, a photon's absorbed, an electron-hole pair are created. The electron's negatively charged and the hole is positively charged. So what often happens is they start orbiting each other and they get stuck inside the carbon nanotube. In the presence of an electric field though, the electron and hole could be pulled apart from each other. The negatively charged electron's pulled one way, the hole's pulled the other. And if that electric field is strong enough, theory predicts that there may be an impact ionization effect. And this is an effect where one electron can multiply and excite more electron-hole pairs as it moves down through the carbon nanotube. And so this is the effect that we're looking for, to try to break that limit of having only one electron come out for one photon being absorbed. So we're experimentalists, and we tackled this by building our own tiny little miniature solar cells from single carbon nanotubes. Here's a scanning electron microscope image of one of the nanotube solar cells that we made. So the light's going to be absorbed in the center of this white string is the carbon nanotube. In the cartoon version, it looks like this. It's a p-n junction with a strong electric field in the middle. And we're looking at how many electrons we get out of this device for every photon that gets absorbed. So on the y-axis, I've drawn this ratio of electrons that we pull out for every photon that's absorbed by the nanotube. And on the x-axis, I've drawn the electric field that we're applying. The first blue dot is showing some of our first data at low electric fields, where a lot of the electrons and holes are getting stuck to each other and not even coming out of the device. It takes 20 photons in to get one electron out of the device. As we went to higher fields, we started seeing evidence that some of the electrons and holes were being pulled apart from each other. So we're getting more electrons out for every handful of photons that are being absorbed. But it's still a lot less than one electron per photon. We had to go to very high electric fields to even get one electron per photon out. And this is where we come on par with what happens in a typical silicon solar cell. But the exciting thing happened at slightly higher field. We could cross this limit of going pulling more than one electron out of the device for every photon that was being absorbed. So does this mean we beat the Shockley-Quasar limit? We haven't come close to having a high power conversion efficiency. However, we have broken one of the assumptions that was used to calculate this limit. So in terms of what next, we should reduce the threshold for electric field to get this multiplication effect. Right now we have to use very high electric fields to multiply the electrons. The open circuit voltage in our carbon nanotube solar cells isn't very impressive, and we're not utilizing every photon that lands on the device. A lot of them miss the nanotube or don't land in the center where the electric field is strong enough. So while we work on these challenges that might sound a little engineering, we are also really enjoying the physics, because pulling apart electrons and holes is a lot like pulling apart hydrogen atoms. In the 1920s, researchers ionizing hydrogen in high electric fields were having a fantastic time working out the details of quantum mechanics. And so we get to relive some of that excitement, pulling apart a slightly different object, the electron-hole pair, inside of a totally new material, the one-dimensional system of a carbon nanotube.